So this is an example of an upper air chart. This is valid at the same time as the surface chart with the other video. What we're looking at here is the equivalent pressure of 500 millibars, or about halfway up the atmosphere as far as pressure is concerned. So approximately half of the atmospheric air is below you and half of the atmospheric air is above you at this level. The lines you see on here are the lines of equivalent height at that pressure level. So if you're flying in a plane and it reads a pressure of 500 millibars, this is how high you would be off the ground. The reason why these lines are different and they're not all the same location is because the atmosphere changes in areas where it's colder, as you can see up here in the central US. The air is more compressed as air gets colder. It gets more dense and it compresses down, so that you don't have to go as high up to get to 500 millibars as you do down here where it's warmer and more tropical. You can see exactly what the heights are in meters with these little purple lines on here. Remember on the station plot that this represented the surface pressure. This represents the height with the leading 5 dropped off of it. Or no, apologies, the last 0 is dropped off of it. So this would be 5,380 meters at this level. This would be 5,400 meters, etc., etc. This would be 5,750 meters down here. Otherwise, this is just like the station plot of the surface. You can see minus 37 degrees Celsius instead of Fahrenheit, minus 40 for the dew point, and then wind out of the northwest at 15. These winds here, these solid triangles, represent 50 knot winds. So in this case, you have a 50 knot one plus a 10 knot one equals 60. This one is 50 plus 10 plus 10 is 70. So you get an idea that the winds are more intense aloft. As you know, this is getting up closer to the jet stream at about 18,000 feet above ground. So the shape of the flow here, when you're doing weather forecasting, this kind of general dipping down and then going back up, we call this a trough. Anywhere where the air does the opposite, you have a little bit of one here where it goes up and then comes back down, is kind of called a ridge. We look for these features because they cause different weather patterns at the surface. When the air is flowing down into the trough here, you can see how the lines kind of pack together really close, because this cold air is pushing down into the more tropical air, which is down to the south. Because of that, the air tends to kind of pile up and push together here, and that causes what we call convergence. The convergence forces the air downward, and when it does that, it forces the pressure at the surface to rise. So in this location, you'd get a high pressure, and you'd tend to expect favorable weather that you would normally see with a high pressure. On this side of the system, the air is spreading out as it comes out of that trough, and it's just like, you can think of this trough like a kink in a hose, where the water was all piling up here, and now it's spraying out onto this side. And as it does that, the opposite thing happens, where as this air spreads out, it sucks up the air below, and it causes the pressure to lower at the surface in this location. And if you recall from the surface video, that we had a low pressure system located right here in Illinois, which is it's there because of what's going on here at the upper levels where this trough is located.